Hey guys, it's Mr. Sheeline here. This is going to be me walking through the Unit 6.1 notes, the notes concerning molar ratios. Okay, so I'll just understand that most of the stuff that we're going to be writing, that you guys are going to be writing in these notes, is just to like prove a point, to show certain ideas, and that you can reference back to in understanding why we're going to do what we're going to do. Should be obvious when we get there. And I'll explain, highlight all that good stuff of what is the most important things to recognize and to know as we go through these. Okay, so anyway, just keep that in mind while we go through this. So what is a molar ratio? So basically a molar ratio, shoot man, I mean just think of it, break it down, it's some sort of comparison between the number of moles from one substance to another, and that's pretty what it is. The ratio of moles of a substance, whether they're reactants or products, in a balanced chemical equation, and they're created by using coefficients. Okay, so that is what a molar ratio is. Well, how is it that we can come to that conclusion? You know, that's the question. How is it that we can come to the conclusion specifically of these being created as coefficients? And that's what we're going to prove right here. Okay. Now, before we do that, though, let's remember this super duper important rule. It's that 1 mole of any substance, out of any substance, okay, there are 6.02 times 10 to the 23rd particles. Okay, always remember that. This is like the key conversion factor that you have to remember, especially when we get to 6.3, when we get to stoich. Shoot, or actually that's 6.2 when we get to stoichiometry. Sorry. So anyway, we also need to remember this, that when we are working with just atoms, and we're converting, say, from moles to particles, can't forget that atoms are referred to the single elements. Ionic compounds, we refer to them as formula units, and then we refer covalent compounds to molecules. Okay. So, and remember, this is a metal plus a nonmetal. These are nonmetals plus nonmetals. Okay? Okay, so just a quick rule to remember. So, okay, so proving this point right here, we're going to prove that point right here. So let's say that we have this equation, that we have hydrogen gas plus oxygen gas that creates H2O. Okay? Also, it is balanced, so we've got 2 H2O. There's nothing in front of the oxygen, which just means 1, and then a 2 in front of the H2O. Okay. So what this tells us here is that it tells us that there's a ratio even here, that there are 2 molecules of H2 hydrogen gas to every 1 molecule of oxygen gas that will give us and yield us 2 whole molecules of water. Okay. So, however, though, we're looking at this in the term of these being these coefficients. These coefficients represent a number of molecules. Okay, and so because of that, okay, arguably we would have to convert these coefficients that represent number of molecules, we would have to convert that from particles, to moles. Okay, so let's do that. Let's just see what we get. We're going to convert these 2 molecules of hydrogen gas, this 1 molecule of oxygen gas. We're going to convert those into moles and see what we get. So we're just going to do what we've always done with molar conversion. So 2 molecules of H2 over 1. We're going to convert these to moles. So divided by 6.02 times 10 to the 23rd, just particles. Oh my goodness, if I could spell. Oh my goodness, oh my goodness. And it's going to be, and again, remembering this rule up here, in every 1 mole of any substance, there are 6.02 times 10 to the 23rd particles. It's Avogadro's number. And we would say then, for here, we would say, well, there are 3.32 times 10 to the negative 24th moles of hydrogen gas. Okay, cool, really big number, not liking that, but cool. Okay, so let's do that with oxygen now. So there's 1 molecule of O2 we're going to do the same thing, convert it to moles. And what we would get here is that there's 1.66 times 10 to the 24th, negative 24th molecules of O2. Now, this kind of stinks because I really don't like the fact that these two things are ginormously small. Okay, ginormously small in the sense that, like, it's 3.32 times 10 to the negative 24th moles. Like, that's insanely small number of moles. Okay, and I really don't want to have to work with that all the time. I don't want to have to do this. So let's do this. Let's try to express that the number of moles here to here. Let's see what that ratio would look like. So as you would with any ratio, we'll divide this by this. So we'll go 3.32 times 10 to the negative 24th divided by, we'll say moles, of H2, divided by 1.66 times 10 to the negative 24th moles of O2. Okay, we'll divide this by this. Well, what we would see here is that we would have 2 moles of hydrogen gas for every 1 mole of oxygen gas. That's kind of interesting. So what we just proved here, what we just saw here is that really we don't have to convert to the actual number of molecules because the ratio of the number of molecules is still the same. Not only is it the same here to here, if we notice this, 2 moles of hydrogen gas, we have a coefficient of 2 up here. 1 mole of oxygen gas, we have 1 molecule of hydrogen gas up here. So, because our ratio matches what we see in our balanced equation, we don't have to do this. We don't have to convert the number of molecules into the actual number of moles. We can just use the coefficients found in the chemical equation, and we can use those in order to convert, say, one substance to another, which is pretty much what we're doing here. Well, converting the number of one substance to the other number of another substance. Okay, so what this shows us is that there really is no need to convert, and this should say, convert particles to moles, okay, in order to get a ratio of the moles in an equation. We can just get the molar ratio by using the coefficients in a balanced chemical equation. Okay, so again, this whole thing up here proves a point. Okay, so you don't have to do this. Don't do this on practice material. Really, you don't have to do it anywhere. Again, all of this right here just proves the point that we don't have to convert the number of molecules, which are based on the coefficients in the chemical equation. We don't have to convert molecules into moles. We can just use the coefficients to say the number of moles of each substance per the balanced equation. Okay, so again, 2 moles of hydrogen gas to every 1 mole of oxygen. Okay, we know that, and we can compare that and say that, well, yeah, we also have 2 molecules to 1, so we could just steal those. Okay, because what matters is the ratio. Okay. So then what's the molar ratio of this equation? Now, you won't ever have questions that ask this, but we're going to just write this out as a way to kind of give us some reference here. So what's the molar ratio? Well, we've got 2 moles of hydrogen gas per 1 mole of oxygen gas per 2 moles of water. Okay. So this would be our ratio. Okay, 2 to 1 to 2. Okay. Now, what do we do with this information? Like, why does this matter? Why do we want to know the molar ratios of any particular substance? Well, it's because you're going to be asked questions like this. Because when you think about it, do you ever get an actual, like, solid measurement of any substance after a chemical reaction? And what I mean by solid, I mean, like, do you get like 3.0? Do you get 5.0? 12.0? No. And on top of that, do you get anything, for the most part, do you get anything that you totally expect? And the answer is typically no, or as long as you being a student and trying, just starting this out. So you'll have problems that look like this. You'll be asked, well, using these balanced equations, how many moles of, say, H2O can be produced from 3.18 molecules of O2? Okay. So you'll be asked questions like that. And so what we're trying to say is, well, using this balanced equation and using the measurement of O2 that you found, or this is what you're putting into this equation, you're going to be putting 3.18 moles of oxygen gas into this equation. How much, how many moles of water is going to be produced, okay, or should be produced? That's what we're doing here. We're converting moles of one substance to moles of another substance. Ultimately, that's what we're doing. Okay, so again, we're starting here and we're ending here. Starting with 3.18 moles of oxygen gas, and we're going to convert to moles of water, of H2O. That's what we're doing. And so to do this, we just do the normal dimensional analysis molar conversion that we've already been doing from Unit 5. So here's the measurement we're given. So we're going to write down that measurement. So our given measurement here, 3 moles of O2 over 1. Okay. So we put that down. Now, it's super duper important, before we move forward here, it's super duper important that every little bit of information needs to be written out. So 3.18 moles of O2, okay, has to be written out. And then everything, all the units, the compounds, the values, everything in a conversion factor has to be written out in these conversion factors because you'll easily become confused of what you're converting between and to. So this is what I mean here. So this is the amount of oxygen gas we're putting in the system, and we want to know how many moles of water will be produced from this amount. So we have to convert moles of O2 into moles of water. So moles of O2, these are our old units, and we're going to be using the molar ratio down here in order to solve for this. So okay, well, I know that between the moles of oxygen gas and H2O, there's 1 to 2. So there's 1 mole of oxygen gas for every 2 moles of water. Okay. And again, the rules still apply. Old units go on the bottom along with your now old compound. So this would cancel out, this would cancel out, and what we're left with is going to be just 3.18 times 2 moles of H2O, which is going to give us 6.36 moles of H2O. Okay. So that's what we're doing. We're taking balanced equations, realizing that the molar ratio is the same as the ratio of the number of molecules between one another, so we don't have to convert particles to moles. We can simply just say that the coefficients are the number of moles, and we use the ratio between one substance and another in order to convert, say, a measurement to a new measurement. Okay? So hopefully this isn't too confusing. Now, if it is, you've got to talk to me, because this is a baby step, because what we're going to be getting into in 6.2 is not just moles to moles, it's going to be mass to particles, mass of one substance to particles of another substance. It'll be particles of one substance to particles of another substance. Okay? It'll be particles of one substance to the moles of another substance. Okay? So here it's just moles of one substance to moles of another substance. So this is our first baby step. And it's also a baby step in the idea that we can say the number of moles in a particular equation per the coefficients in that equation. Okay. Let's just do another problem then. Let's do another example problem. Give me a second here, guys. Okay. So another example problem, we'll say we'll say is this. Okay. So we're going to say aluminum reacts with hydrochloric acid to produce aluminum chloride and hydrogen gas. Calculate the number of moles. Calculate the number of moles of hydrochloric acid required to react with 0.87 moles of aluminum. And then here's our balanced equation. Our balanced equation is going to be 2 aluminum plus 6. It's going to react with 6 molecules of hydrochloric acid, and it's going to yield us 2 molecules of aluminum chloride, and then 3 molecules of hydrogen gas. Okay, so and this is a great question too, to kind of have to see another way that these questions are formed. So aluminum reacts with hydrochloric acid. Aluminum is reacting with hydrochloric acid, and it's going to produce aluminum chloride, and also hydrogen gas. And we're trying to calculate the number of moles of this stuff right here required to react with 0.87 moles of this stuff right here. Okay, so this is what we're going to do. We see that we got to go from here. We're going from here to here. Okay, moles of aluminum to moles of hydrochloric acid. Now to do this, again, start off by writing out our given. We're going to write out our given material, our given measurement, which is 0.87 moles of aluminum, okay, over 1. And we're going to convert moles of aluminum to moles of hydrochloric acid. So in order to convert moles of aluminum to hydrochloric acid, we have to use the ratio, the molar ratio of these guys, using these coefficients. So again, moles are on the moles of aluminum will be on the bottom, moles of HCl, of hydrochloric acid, up top. So what's my ratio? Well, there's 2 moles of aluminum to 6 moles of hydrochloric acid. Okay, these will cancel out. That cancels out, and we'll be left with just moles of hydrochloric acid. So 0.87 times 6 divided by 2, it's going to give us 2.6 moles of HCl as our answer. Okay, so, and a quick little brief explanation of really what this means. So in this equation, in this balanced equation, what it's telling us is that there needs to be 2 aluminum molecules that will react with 6 molecules of hydrochloric acid, which will produce 2 molecules of aluminum chloride, and then 3 molecules of hydrogen gas. So if we need 2 in order to react with the 6, what we're saying here is that if we only have 0.87, well, how many moles of HCl is going to react with the 0.87? And in order to find that, we have to convert using the ratios that we see here. Okay, so that's what that is. This is the amount of moles that will react with what we're putting into it. Okay, so since we don't have 2, and since we don't have 2 here, we only have 8.07 or 0.87. Sorry, that 0.87 is just going to react with just 2.6 moles of hydrochloric acid. Okay. Now, last thing that I'll mention is that when we're solving for this, you've got to show all your work. So we still need to see all this work, still need to see all this dimensional analysis. Also have to keep sig figs. So notice I started with 0.87, that's 2 sig figs. That's 2 sig figs. And I'm going to produce my answer that only has 2 sig figs as well, even though my calculator actually gave me 2.61. Also, need to always include the proper units. Okay. Also, need to include the proper compound. So this really hasn't changed at all from Unit 5. Still need to show me all this work, still need to keep sig figs and correct value. Okay. Still need to show me the units, still need to show me the compound. Okay. So still need all that. And actually, last thing, because I mentioned it and I didn't come back to talk about it. This is why it's important, again, that we have to make sure that we include all of our units and compounds that we're converting between. So here, moles of aluminum, 0.87 moles of aluminum, 2 moles of aluminum, 6 moles of hydrochloric acid, because we want these to cancel out, and we want to make sure that we're ending with the stuff that we want to end with. Okay. Oh, and last thing. So I'm also probably thinking that you guys are like, well, wait, Mr. Sheeline, don't we have like a 2 to 6 to 2 to 3 ratio here? How can we only focus on these two? Like, what happens with these two over here? Why don't we care about what's happening over here, what's being produced? Don't those ratios affect anything along with everything else? No, they will be affected by the amount that we put in, but do we have to take this in account when we're converting this number of moles to these number of moles? No, we don't. We can just ignore that. We just have to know that we're going from this to this, and we have to make sure that we include all the units from this to this, which in this case would just be the molar ratio. Okay, we can ignore these because we're not worrying about those. Well, we're not converting from aluminum to aluminum chloride. Okay, we're just converting from aluminum to hydrochloric acid. Okay, so don't confuse yourself. Don't think that you have to worry about the coefficients over here. Okay, in this problem. Okay, in this problem we didn't have to. We just had to worry about this one and this one. Same thing goes down here. Like when in this problem, how many moles of water will be produced from this number of moles of oxygen gas? Like, yeah, we only worried about these two guys. We didn't worry about the number of moles of hydrogen gas. We don't know. It's not part of the equation here. Just this to this. Okay? So if you guys still have any questions for me, make sure that you ask. This is no different, okay? This is no different from, my message from Unit 5. We've got to take this seriously. You've got to practice this, because this right here is the baby step before we get to stoic. And stoic is a doozy. And then after stoic, we're going to be getting into limiting reactants, where we're going to be using something called BCA chart. And that is a doozy. You've got to take this seriously. You've got to practice. You've got to do all the steps, or else you will be behind. Okay? And if you experience that in Unit 5, I'm telling you right now that, again, you will not succeed if you do not keep up and if you do not do the practice and put in the time. You will be sorry in that sense, that you will be super behind, you'll be playing catch up the whole time, and you will not have any clue of what's going on. Okay, so you've got to ask me, like, as soon as something is confusing, you've got to ask me. Okay, ultimately that is what I'm saying here. You've got to tell me that you don't understand something so I can help you understand it. Because again, if you don't understand this, you're not going to understand stoic. Because you have to understand this before we can understand what stoichiometry is, okay? So anyway, if you have a question for me, if you need to come in on Fridays, remember that's still an option. You can come in on Fridays for extra help. You can come in after school. I'll let you know that it's possible that soccer season, we're going to see what the soccer season looks like, but I'm going to be at practice after school, and that's going to make it really hard for me to get back on emails, and that's going to be really hard to get back to you on you coming in for extra help. So you've got to be on top of this, and you've got to be working with me to get in time for that extra help and that extra practice. Okay? Also, you've got to be following along with the notes. You've got to be using the notes as a resource. We don't just fill these out so that you just fill them out and you just put them in your binder. This is a resource. This is what you use in order to help you answer problems in the practice material. Okay? So reference back to this. Reference back to specifically, in this case, just this stuff, in order to know what's going on and to how to set this up And now you even have like an extra problem here to help you, to help give some context. Okay. So anyway, that's it for the video here, guys. Again, get a hold of me if there's something you don't understand. And if not, I will see you in the next one.